Welcome everyone, I'm Josh and this is JSURS, and today I'm going to show you the assembly and testing of some simple electronic circuits. They should be of interest to everyone. As I had mentioned before, I was planning to show you some circuits that'll demonstrate the basics of electronics. This one seems fairly interesting in my opinion. It involves a simple square wave generator attached to an amplifier, and we'll be looking at the signals at various points in those circuits. So for now, just a general overview. You can see my oscilloscope and my variable power supply. I'm just going to hook right up to both the square wave generator and the amplifier. Now a closer look at these things. So as you can see, we've got our power supply connected to those points there. They're connected to the top rails that feed all the circuits. And we've got our square wave generator there, which then feeds through there into our amplifier. And you can see we've got that lead connected there right before the amplifier and that second one after the amplifier. Now an even closer up, this is the 555 timer based circuit that we've got going here. A lot of you will recognize that integrated circuit in the center. Basically, we have it configured as an astable multivibrator, which basically means it will create an oscillating signal of some kind, in this case a square wave. Now you can see we've got our signal rail down there. I realize it's labeled like a power rail, but the lower one is being used as a signal rail and doesn't actually have power applied. The upper two rows have the power on them. Now over here we can see our simple single transistor amplifier a bit better, but in the middle here what we've got is two jumpers going from the power rails at the top to the power rails in the middle there. And we've got our positives and negatives hooked up to all the correct places. The color coding is not really color coding because these jumpers are color coded based on length, not based on polarity. So I apologize for any confusion that may cause. Now as we go up a little bit, we can see the power rail a little better. As you can see, our positive is going into the amplifier through that resistor there, and the lower rail there has the signal traveling from the amplifier over to basically a point where it's convenient to hook up our oscilloscope lead, and we're also going to be plugging an LED in there. So we've got our signal there, and then over there, attached to the negative of the power supply, we've got our signal ground, because that's the reference for our whole system. Now this is just an overview of everything a little closer up. And next we're going to be looking directly at the waveforms without so much focus on the actual components. So we've got our leads hooked up in the same places they were before. I'm just going to show you the boot up sequence for the oscilloscope. And once that's all booted up, I'll explain a few things and we'll turn on the power supply and we'll see how the waveforms come to be, basically. Alright, so the oscilloscope has started up. You can see that there are two horizontal lines on there. Those are our two signals. This is a two-channel oscilloscope, so it can have up to two signals on the screen at once. Just plugging in my power supply there. Now it's set to 0.1 volts right now. That's the lowest voltage this thing will put out. It's basically nothing. But as we turn it up, you'll see that the lines start moving, and then, oh look, there's the square wave. Now I usually set this kind of circuit to around 10 volts. Theoretically, it can handle up to 15 or 16 volts. I believe that most 555 timers can go from 15 to 17 volts maximum. Now, as you can see, the yellow lines conform to the first channel, the blue lines to the second. And they look very similar in size, but that's deceptive, as you'll see later. Now that we're zoomed in a little bit more, hopefully you can read the screen better. And as you can see, channel 1 has a 200 millivolt per division setting, and channel 2 has a 5 volt per division setting. So even though these waveforms are the same in amplitude, they're actually very different when you consider the scale. Now I just hit the auto button, and basically that tells the oscilloscope to do its best guess of what the settings are that it should do for those waveforms. And next we're going to select one of the channels and show you that we can adjust it vertically. I'm not going to bother adjusting the time scale. Basically the time scale just changes how you perceive the horizontal displacement. And it's set pretty well right now, so I'm not going to mess with it. Now what I'm going to show you next is what happens when we lower the voltage. It starts to go a little crazy around 8.7, but when we bring it up to the max that this power supply can do, you can see the amplitude of both of them goes up significantly. Now back to 10 volts, and when we turn it off, obviously it shuts down. Alright, next I'm going to do a circuit walkthrough. I'm going to show what this circuit does on paper. I'm not going to go into extreme detail, but this will be helpful and informative for those of you that are more technically minded. I've kept it fairly simple, and I'm not showing the internal workings of the 555 timer, which is the integrated circuit you saw earlier in the video. I'm just going to explain the very basics. I'm not even going to show you any formulas, so you don't need to do math. So a 555 timer, as this thing is, it's an 8-pin integrated circuit. It has many different uses. It's mostly used by hobbyists as a square wave or triangle wave generator. In our case, we're using it as a square wave generator, but you can use it as something called a latching circuit, which is useful in digital electronics. You can also use it as a motor control circuit. It can do pulse width modulation, which is a way of controlling the speed of direct current motors. So there's a lot of different uses to it, but in our case, we're using it as what is called an astable multivibrator. Basically, that just means that it will change state from high to low continuously, as long as power is applied, without requiring any kind of trigger event. And the rate of that change is primarily determined by these three highlighted components: 2 resistors and a capacitor. Those of you who are familiar with electronics will recognize this as part of an RC time constant circuit. And that's exactly what it is. I'm not going to go into the actual formulas right now, but just so that you know, that determines the frequency, basically, of the square wave. And it also can determine whether the peaks and valleys of the square wave will be equal in width or whether they'll be unequal. So, one thing to notice about the 555 timer that we're using as a square wave generator is that it outputs our square wave at a fairly small voltage level. I believe in this case it's about 400 millivolts, but I'd have to go back and look at what the oscilloscope says. And you'll also notice I've tried to illustrate the phase of the square wave. So we start low, go high, low, high, low. That will be important later on, as some of you may have already noticed. So the thing that comes after the 555 timer is the amplifier circuit, which is on this side of the dotted line. It involves a transistor here, And for those of you who don't know, a transistor is basically, it functions like a variable resistor. It can be used either as a simple switch or as a component that varies the resistance between these two legs based on the voltage between these two legs. In our case, we're varying the voltage between these two legs using this waveform, and that varies the resistance between these two legs at exactly the same rate. And this means that the voltage we apply at the top here will be modulated by it, essentially. But because the voltage here provides a larger peak-to-peak voltage at the output, it'll make this smaller signal bigger. Now, as a consequence of how this particular amplifier happens to work, you'll notice that the phase is shifted 180 degrees, and you probably saw that on the oscilloscope when we were comparing the two waveforms. This amplifier is inverting. There are amplifiers that don't invert, but this is a very simple one. Now, the components in this amplifier, there's not very many of them other than the transistor. There's just two resistors here. Now this is the bias resistor, R1, and that basically just makes sure that there's enough of a voltage difference between the collector and the base for the transistor to work properly. And this bottom part here is called the emitter. So there has to be the correct voltage drop there. And the R2 here is just a current limiting resistor. You don't technically necessarily need a current limiting resistor, but it's a good idea. It protects the transistor from overcurrent, as you might expect. Now, let's see. The only thing remaining is the points across which the output is taken. So you'll see that I'm taking my output across the collector below R2 and at the emitter, which, if you follow the line here, you can see is ground. Sometimes there's an additional resistor on the emitter leg, but not in this case. And so we just get our larger signal here, which in our case I believe is a little less than 10 volts peak to peak, and it's inverted. And something that you might have noticed in the sketch here that doesn't really make a whole lot of sense is this crossed out portion with a question mark. So as I was transcribing this from the source I used for the basic circuit, I accidentally put an additional leg on the integrated circuit. That leg just doesn't exist. It's not a real thing. So yeah. Anyway, I hope that this has been helpful, and I hope it's introduced some of you to electronics and how interesting it can be. And if you have any questions or any recommendations for things you'd like to see about electronics in the future, please leave it in the comments down below. And if you'd like to see more of this, like and subscribe. Thank you.